So far we've used Dyson's equation to show how we sort of rederive expressions that we've already derived. Basically, we've rederived our expressions for these self-energies in terms of the surface green functions of the left and the right leads. We calculated the expression for the exact device green functions using Dyson's equation. And now we're going to show sort of how this algorithm in its most general form is actually used. And so the first thing is to divide up your device and leads in a certain way. So we'll take our generic double barrier device. It's resonant, some kind of resonant device that you're working on this simple model for in this homework. And so the band diagram would look something like this. My device, this will be my device region. And it's going to go from the usual node 1, 2 to node n. So there'll be n nodes in my device. My leads get divided up in a funny way that we haven't seen before. So there's going to be two regions to the leads. I've got 0, -1, -2, and then the semi-infinite rest of it, -3 to -infinity out here. And the same thing over here. Say there's 3 nodes, n plus 1, n plus 2, and n plus 3, and then n plus 4 to infinity out here. All of this region is an equilibrium region, and it's in equilibrium with the right contact. And this region out here is flat band in the same way we've been thinking about a lead. So all the electric fields, there's no band bending out in this region to the right of that dashed line. In this region, we're going to allow band bending. So here we will allow band bending, which means non-zero electric fields, just the way I've drawn it. But nevertheless, we still consider it to be in equilibrium with the right contact, with the occupation defined as E, F of E minus the chemical potential or Fermi level of the right contact. And of course out here also the same thing. The filling of these states is just determined by the Fermi factor of the right contact. And so the same thing holds true over on the other side, where here all of this is considered to be in equilibrium with the left contact, and everything, the occupation is determined by the Fermi function or the Fermi level of the left contact. In here we allow band bending, again, which means the electric field is not zero there, but it's still considered to be in equilibrium with the left contact, with the filling of the states just determined by the chemical potential of the left contact. And the device is our non-equilibrium region. In the device region, that's our non-equilibrium region, where the filling is not an equilibrium distribution. It's not determined by an equilibrium Fermi factor. The filling I mean, to get the charge density, we have to calculate G sub n in the same way we talked about in chapter 1. So that's the setup. Yeah.
I'm thinking about the band bending region. There is potential. So why this is non-equilibrium?
Because to a very good approximation for this kind of problem where you have a big barrier like that separating the left region from anything else, all those states are going to be determined, are going to be, if you think of what determines the charge density, you have A left times F left plus A right times F right. A right is just the magnitude of the wave function squared injected from the right. Not much of that is getting all the way through both barriers to the left. And so to a very good approximation, the states there are determined by, the filling is just determined by your left Fermi factor. When you have some kind of barrier, decent barrier that's separating the left and right half of the problem. And I guess we could also call all of this region our source, and all of this region our drain. Okay. And so again, if I just separate out the band diagram, it's getting kind of messy. I would have something. Some band bending, some barriers. A little more band bending flat. And so we're just assuming that the occupation out here in the left and the right is given by mu left and mu right. And in the device region, the non-equilibrium region, we have to figure out what the occupation is. Okay, so as usual, we need current and electron density. That's what we're after in the device. Well, also in the band bending region of the lead. So both in the device and in the band bending region of leads. In a real device simulation, would have to be iterating this with Poisson's equation to get the potential correctly. So you'd be calculating the charge, sending it to Poisson's equation to get a new potential, and iterate until convergence. And to do that, you need the electron density anywhere where there's potential variation occurring. Okay, so this is what we want to calculate. So we're going to start on the right-hand side by calculating the surface green function of the semi-infinite right lead. I guess the semi-infinite, so the semi-infinite part is the part in flat band. After the band bending, all the flat band, the semi-infinite region that has no potential variation. And since it has no potential variation, we use to calculate this, and so specifically what I'm talking about is G right connected n plus 4 comma n plus 4. That's the surface green function at the end of this flat band region on the right. And so you calculate that using any of the methods we talked about in, I guess, chapter 2. Right? Like dim, decimation, mode space. So the starting point is getting your surface green function using any of those methods from chapter 2. And then the terminology is that you walk this surface green function, or you walk the right connected green function across your device to and including layer 2. what I need to layer 2. All right, layer 2 was the device started at layer 1. So how do we do that? What algorithm do we do to move the right connected? Well, we already saw how that works. So G right connected, we have n plus 4, so n plus 3, n plus 3 is just equal to E. Now we're in the band bending region of the right lead. Okay, so we're moving into where things are changing as a function of layer number. So E minus D n plus 3 minus T n plus 3 n plus 4 G right connected n plus 4 n plus 4 and T n plus 4 n plus 3 inverse. Right? This is exactly the form we had when we, on our example 1, when we had the green function at 0, 0, and we added on one node to the right. Now we have the green function at n plus 4, n plus 4, and we're just adding on one node to the left. And this is the exact, when you do this, you just pick up a term that looks like the self-energy due to your semi-infinite lead, right? This is your self-energy due to the semi-infinite lead starting at n plus 4.
Why can't we calculate the Gn plus 3 n plus 3 from the dim
From the what?
down iterative algorithm?
Because you have band bending, and dn plus 3 is not the same as dn plus 4. You're no longer in something that's periodic. You had to rely on the fact that everything's periodic to do the dumb iterative algorithm. Right? In that case, Gn plus 4, n plus 4 was identical to Gn plus 3, Gn plus 3. Now it's not, because things are starting to change. That's why we divided. I carefully divided up the system like this. So all those algorithms in chapter 2 rely on the system being periodic, nothing changing from unit cell to unit cell. As soon as we leave these flat band regions, that's no longer true. And so in general, we just moved it 1, but in general, the recursive algorithm is that G right connected J comma J is equal to E minus D JJ minus T J J plus 1 G right connected J plus 1 J plus 1 T J plus 1 comma J, the whole thing inverted. And so you just keep moving across the device like this until you get to layer 2. So G right connected 2, 2 is E minus D22 minus D2 T23 G right connected 3, 3 T32 inverse. And so now you've created the right connected green function all the way to and including layer 2. And I guess we should, since this is a general expression, this is a generic expression on how we move the right connected green function one side to the left. Okay, the other important thing when you're doing this is that only in the lead regions So only in these regions of the leads we're assuming they're in equilibrium. Throughout all here, are you allowed to have a finite imaginary term, E minus H plus I eta, when you do this. So throughout these regions, and in the device, in the non-equilibrium region, eta must be equal to 0. If eta is not 0 in the non-equilibrium region, then you won't conserve current. So when we're doing, so what that means in terms of what we just did here, for all the D's, the diagonal blocks that are in these equilibrium regions, to the left and right of the barriers, we can put an I eta on the diagonal elements, and that will give energy broadening, and it will do other things for us that we'll talk about later. But in the device, eta must be equal to 0, and that's non-equilibrium region. So to be very specific, for sites 1 to n, eta is 0. So for sites 1 to n, eta must be equal to 0. And for all the other sites, you can have some imaginary term on the diagonal, which can serve various purposes that we'll talk about later. Eta is 0 for sites 1 through n. And so, for example, in this block here, could include, you know, a E minus D, a minus, I don't want to confuse the sign, but dn plus 3 could include like a negative I eta times the identity matrix in there. A negative I eta on the diagonal of the D matrix. Okay. So that takes care of the right lead. We've moved that all the way across the device. So now the flat band region of the left lead starts at -3, and so we'll go ahead and calculate the surface green function of the left lead at -3, again using any of the methods from chapter 2. That'll be our left connected green function at -3, -3. Again, using any of the methods from chapter 2. And we walk this left connected green function to site 0. Again, using the same type of recursive algorithm. So the generic one is that G left connected at JJ is equal to E minus D JJ minus T J comma J minus 1 G left connected J minus 1 T J minus 1 comma J, whole thing inverted. So this is a generic equation for moving the left connected green function across your device, moving it one node to the right. And so now we have, so we started at -3, -3, we move it up, so now we have G left connected at 0, 0. We have G right connected at 2, 2, right? Right, because we walk the right connected guy across the 2, 2 down there at the bottom. So we walk the right connected all the way across the entire device. We just move the left connected up from -3, 3 up to 0, 0. using this. This is what they call the recursive green function algorithm. And so now we can get the exact green function at 1, 1. So the exact green function that includes everything at 1, 1 is just equal to E minus D 1, 1 minus T 1, 0 G left connected 0, 0 T 0, 1 minus T 1, 2 G right connected 2, 2 T 2, 1. Whole thing inverted. And this is exactly the form we had when we used Dyson's equation to calculate the green function of the entire device. In this case, we've reduced it to formally to a device of just one layer, 1, 1, and we get, our usual self-energy due to connecting to the left and the self-energy due to connecting to the right. But these are no longer ideal leads we're connecting to. That right connected green function at 2, 2 is a surface green function, but includes the effects of all the band bending and whatever is going on to the right to and including from site 2 all the way to plus infinity. It includes all that, whatever is going on, whatever band bending is occurring over there. And the left connected to 0, 0 includes everything from 0, 0 back to negative infinity, whatever band bending is going on there. So they are surface green functions because they are at terminated surfaces, but they're not of some ideal crystal, because they include the effect of all the band bending to the left and right of them. Okay, so these are the three so far, these three equations in red. This is a generic one for moving the right connected over to the left, the equation for moving the left connected over to the right, and finally you get the exact green function at G11. And remember, to get the current, this would be all we need. This would be all we need if we want the current. The first block of the green function was all we need to get the transmission. So if we only needed transmission, we would stop here. You're done. You can go ahead and calculate transmission at this point. If you need the electron density, you have to keep going, because you need more stuff. For electron and hole density, we need the exact diagonal element of the green function in the device, and we needed the first block column. The first block column. So we need all the diagonal elements in the first block column to get the electron or hole density. So let's work on getting let's get the diagonal elements. Okay, and to do this, so we have G11, right? G11 is our starting point. So we need to get, G22, G33, etc. So we have G11. We need to move this thing to the right. And so we write a Dyson's equation with the V, non-zero elements of V, being T, J, J minus 1, and T, J minus 1J. If I want to move, well, let's just write it down. So the generic equation to move this forward is a G, JJ is equal to G right connected jj plus g right connected jj t j j minus 1 exact g j minus 1 j plus g right connected j comma j minus 1 t j minus 1 comma j and the exact g j j. Okay, but the thing, you know, for the bare g's, the small g's, we've set the tj j minus 1 to 0. So again, this guy is 0. For the same reasons we talked about before. Anything that crosses the j minus 1 boundary for the bare g's has got to, for the small g's, has got to be 0. And you know, so these, if you think of what I'm doing here, I've got, let's just start with like my starting point, 1, 1. I had the exact g that includes everything, right, at 1, 1.
Sorry, Professor, but why if that's 0? The j and j minus 1 both are in the device?
Oh, well, I mean, the v, right? The little g's are always calculated with these terms set to 0. The little g's are calculated with those terms set to 0. So if there's no coupling between j and j minus 1, there can't be any response. Checked at one and look at the other. They're like in two different universes. Isolated. No coupling. Oh, I guess I had more terms before I do this. Whoops, what did I just do? Error correction. There's two more terms, which are also going to be 0, but let me write them out, because it's good in the beginning to, because it's so easy when you start playing with this yourself to forget terms. So it's, if you're doing something new, some new derivation, it's always good to just write out every possible term and then figure out what's 0. So the left connected, jj, tj, comma, j minus 1, big G, j minus 1 comma j, plus left connected j minus 1 t j minus 1 comma j, big G jj. Okay, for the same reason that the left connected or the right connected j minus 1 was 0, this guy is also going to be 0. Because it crosses that boundary. The interesting case is this guy here. What about this guy? It doesn't cross the boundary. So what? Is it 0 or not? So there's no coupling to the left. So there can't be a left connected green function if there's no coupling to the left. I never thought of the possibility there could just be a bare. No, that's not a possibility. Because this is where this is when things get really tricky, and you have to really understand what you're. Because what we're looking at is this. Let's see. What are we really looking at? I've got j and j minus 1. So here's j. Here's j minus 1. And I've got these two semi-infinite systems, right? J minus 2, J minus 3, J minus, where everything is included. All these other t's are already there. The only thing I'm dealing, doing with my Dyson's equation is now including the t j minus 1, j, and j minus 1. But all these other sites are already, the effect of all these other sites are already included. So the only possible kind of like little g's you can have will either be the left connected or right connected green function. At first I was wondering, well, couldn't this just be like the truly bare g, which is just includes, E minus dj inverse. Like this site energy alone and nothing else. But no, I can't do that because this has to be the green function of this entire thing, because it has to take into account all this stuff. There is no, little bare or green function, just E minus D anymore. Because the only thing that I'm, breaking and reconnecting are these Tj, j minus 1, and Tj minus 1, j. And so this is where this notation becomes really important, and you really have to like draw out what the system is, which element you're like breaking and adding back in through Dyson's equation. So the only non-zero terms we get are those first two terms. Okay, so given that, then we have to write as just as before. So now we've got this. All that, we've got that. And we have to write another Dyson equation for that, the thing that crosses the boundary. So G, j minus 1 comma j is equal, and so now for the first time, we're going to use the alternate form of Dyson's equation to close these. So this is equal to big G, j minus 1, j minus 1, times T, j minus 1 comma j, times right connected G, j, j. And the reason I have to do it that way is that I could also write it like this. G left connected, j minus 1, j minus 1, T, j minus 1 comma j, the exact G, j, j. The problem is, if you recall, we only know this up to site 0. The way we set this up, and we're trying to like reduce this to the least number of calculations possible, because each one, if you're dealing with block matrices, to get every green function here is an inversion of a matrix, which gets to be time consuming and computationally intensive. So if we only have the left connected one up to and including 0, 0. We don't have them beyond that. What we do have are the right connected ones for all JJ up from starting at 2 to all the way across. So we're going to write it in a way making use of what we have, and we have this, right? This is just from our previous, like starting at 1, 1. This would be, we already have the exact one at the node to the left of us. We're trying to get the one to the node to the right. So if we write it like this, we have all the information we need. So we put this back into this equation here for this term. So we just put that back in. And we finally get the equation that we actually implement, which is G, JJ is equal to the right connected JJ plus right connected JJ T J J minus 1 big G J minus 1 minus 1 T J minus 1 comma J and the right connected JJ. Oh, yeah, that's it. So this is an exact expression given that you have this, and the starting point will be your G11, then you do this once and you have G22, et cetera, you move it across. There's not much you can do to simplify it. You could factor out that G right connected. If you want to do that, you might save yourself a matrix multiplication. So depending on how big your matrices are, you're always looking to save either multiplication, inversion, anything you can. And that's about as much as we can do with it. Note this is the first time we're not inverting anything. Right? We're not inverting anything here. There's no inversion involved. The inversions were involved in getting the full G11 here in the usual form, but now that when we're walking G1, the exact green function, the diagonal blocks back across the device, we get this expression because we use this alternative form of the green function, of Dyson's equation, the top line instead of the second line. If we'd used the second line, we would have gotten an expression we could invert. But with this one, we just get this sort of multiplicative expression to go from one diagonal G to the next one to the right of it. And going through the same, I mean, the form is going to be the same. Well, let's see. So this would be all the J. So this is going to give me the exact diagonal block for all J's. I mean, for all J's. I already have J11 for J equals 2 through, I will need it through, what was my numbering system here? Through n plus 3. So I get my exact diagonal green function for all layer 2 through n plus 3. I'll also need the exact diagonal green function for this region in the left where there's band bending but in equilibrium. So for nodes -2, -1, and 0, I'll also need my exact diagonal blocks to get the, because I need the density of states. I know the filling, but I'll need the density of states or the spectral function to get the charge. So I also need the exact diagonal blocks there. And so in the band bending region of the left lead, I also need the diagonal block. So there, again, what I know is G11, so now I need to move it back to the left. But in that region, I do have my left connected green function. So I have G JJ is equal to left connected JJ times the identity plus T J comma J plus 1, the exact green function at J plus 1 times G left connected J. Again, no invert. It's exactly the same form of what we had moving to the right, except I replaced, wherever there was a right connected, I replaced a left connected, and now the indices are moving one back instead of coupling something ahead of it to something behind it instead of the other way. So again, my starting point, what I know initially is I have G11, and so I'd use this to get G00, G minus 1 minus 1, G minus 2 minus 2. So I'd use this first set of equations to get that corner block G11. Then I use these expressions to move that diagonal block to the left and the right. And so, there's a lot of, if you look at what we've done and think about how this algorithm would work, you calculate all the right connected green functions across the entire device. As you calculate them, they have to be stored and saved because I'm reusing them for this algorithm here. All right, as I calculated all those right connected, where's the right connected guys? So the very first thing we did here, calculating these right connected green functions and moving them, walking them all the way from the right lead across the device, they all have to be stored because I'm going to reuse them. Okay. And so if they tend to be big blocks, that gets to be problematic. I do it for the left connected ones, but I'm only moving them a little way. I don't have so many of them. And then they get reused both for the calculation of G11 and then for this Dyson equation that moves the diagonal block both to the left and to the right. So here we're moving to the right, and over here we're moving to the left. Okay, so now at this point we have all our diagonal blocks. That's good. We still need that left block column, that first block column of the non-equilibrium region. So we need the first block column of the non-equilibrium region. Again, the non-equilibrium region is that region from 1 to n, which means we need the exact G of I, comma 1, what we need. So again, the way we attack this is we write a Dyson equation. So we're going to write a Dyson equation that relates G, J comma 1 to G, J minus 1 comma 1. Because we have G11. Everything starts with G11. We have G11, so we're going to write a Dyson equation to get G21 and G31 and G41. And that Dyson equation is G J1 is equal to G right connected JJ T J minus 1 and the exact G J minus 1 comma 1. So again, your starting point is first thing you're going to get is J21. So if J is 2, then the term on the right is just your G11, which you know. So first this would be your G11. J is 2. So you know you're right connected at 2, 2. You have everything you need there. And again, the V, the non-zero matrix elements are the Tj, J minus 1, and Tj minus 1j. And I guess I could say write out all the other terms and see that all the other terms are 0. This is the only non-zero term you're going to get in this Dyson equation. And so if you start writing this out for all the terms, you're going to get G21 for the whole column. G21 is going to be your right connected 22 T21 G11, right? And then G31 is your right connected 33 T32 G21 dot dot dot. So GN1 is going to equal G right connected NN TN N minus 1, the exact G N minus 1 comma 1. So now if you look at the way this works, each time we're using, the one behind it, it gets fed into the next one. So what you calculate in the previous iteration gets fed to the next one, and you just go right down the whole column. And this is sort of, at least in the recursive green function algorithm, sort of the minimal number of steps to get what you need to get G11. That's our starting point. All the diagonal blocks, GJJ, and that first column, GJ1. And with those, you can calculate your transmission and your charge density throughout the device. Okay, so there's, in the notes, see section 4.3, which just summarizes a set of equations that we just went through. An equation for G the G left connected, G right connected, the exact G11, then the exact GJJ, and finally that first column, GJ1. So that's a set of equations you need that constitute the recursive green function algorithm the way we use it. There are other forms, but this is computationally most efficient in terms of the minimum number of calculations that you need to get exactly the blocks that you need to calculate current and electron density. And then, so we've got these different regions. We've different, we have the non-equilibrium region and these two equilibrium regions, but where there's band bending. So we actually have to calculate the charge, even though there's in equilibrium, because there's band bending. And so the way we calculate the charge in the non-equilibrium region is different from the way we calculate the charge. So just let me go through, given the fact that we've got all these G's, the diagonal G's, first block column and all that, how we use them to finally get, what we're finally after. So in region 1, let me see if I labeled them back here. So region 1, make sure this is the same. Yeah, okay. So this region here, where there's band bending, but it's still in equilibrium with the left lead, is region 1. This region over here, calling region 2, and the device region is just the device region. So we need to calculate charge in regions 1, region 2, and in the device. The flat band regions of the leads we don't. Okay, so in region 1, which is where you have band bending in the left lead. Well, since it's in equilibrium, we're going to use the equilibrium expression to get the charge. So in equilibrium, this correlation function which gives us the electron density, Gn Jj, is just equal to your spectral function times the occupation of the left lead. So this is the equilibrium relation, and we're assuming that this part of the lead is in equilibrium with the filling determined by that Fermi factor. And similarly, if you want the hole density, it's the same deal, which is -2 imaginary G times 1 minus F. And so in these, so this is in our numbering system, this was for sites J equal to -2, -1, and 0. For our specific example, right, just to be absolutely clear. And so, just to recall, Nj was just equal to integral dE over 2 pi. If Gn is if Gjj is a block matrix, then you would trace over it. Gn Jj. The trace just means sum all the diagonal elements. And if you want to turn it into a density, then you probably divide by a volume associated with your lattice constant. So in 1D we had 1 over A, and 2D you'd have 1 over A squared, 3D 1 over A cubed. And the same thing is true in region 2, which is the right lead, the exact same form. In region 2 you do the same thing, except you just replace mu left with mu right. So again, you use the equilibrium expressions. The filling is just given by the Fermi factor with the chemical potential of the Fermi level of the right lead. And the same thing for the holes, you just replace F with 1 minus F. Okay. The same form. And then in the device, we have to use our non-equilibrium expressions. So the device, our nodes 1 through n. So region 2 was our n plus 1 to n plus 3, I guess. That was region 2. So in the device, nodes 1 through n, we have to use our non-equilibrium expression, which is G and Jj is equal to G, J1, gamma 1, 1, G, J1 dagger, times F of E minus mu L minus F of E minus mu R minus 2 imaginary G Jj times F of E minus mu R. Right, this was our expression for the non-equilibrium correlation function Gn. This was our numerically efficient form. We got this, initially we just had A left times F left plus A right times F right, but A right required like the other column, the right column of the green function, and we want to only calculate one column. And so this is, here, over here, this is our first column. This is just the dagger of the first column blocks. So all we need is the first column and the diagonal blocks over here to get the charge density throughout the non-equilibrium region of the device. The gammas, well, what are the gammas? The gammas are the usual things. So gamma 1, 1 is just an I times sigma minus sigma dagger. Sigma 1, 1 minus sigma dagger. And these sigmas are your T10. And here, I guess that superscript R just is your retarded self-energy. I haven't been using that up till now because there's been so many other superscripts. That's the retarded self-energy due to coupling to the left lead. And that's the only one we need, I guess, because we're using this numerically efficient form. We don't need gamma right anywhere, looks like. Right? Because if I wanted I guess I didn't write down the transmission anywhere. This is all for calculating the charge density. Transmission is just our usual numerically efficient form for the transmission. And then I say this is my right connected spectral function, which is equal to my full spectral function minus my left connected spectral function. So that's equal to gamma 1, 1 times A minus G 1, 1 gamma. Gamma 1, 1 GA 1, 1. That's the form I'm looking for. So this is equal to gamma 1, 1 times A, which would be negative 2 imaginary G11 minus G11 gamma 11 G11 dagger. That's why we said, if you just wanted current, which means you just need transmission, the only thing you need is G11. And so that's the recursive Green function algorithm. That's the way we, if we have any problem that's not numerically trivial, this is the way we go about calculating what we need to get the Green functions in the device, the transmission, and the electron density. So I guess that brings us to the conclusion. So we'll have a discussion section this Friday, again at 1:10, because every Friday I have this meeting at 12:10. So 1:10, is that okay for everyone? Okay. So do you want to have another discussion section before the homework is due? I know the answer is yes. Why do I even ask? Okay, so we'll have a discussion section Friday. I won't be here Monday, so then I guess we're going to have the makeup lecture next Friday. So the Friday, whatever that is. So Friday after next Monday. We're going to use that time, I guess, went from like 1:10 to 4 to do the makeup lecture. But for now, we'll have a discussion section next Friday at 1:10 here. And so I guess the homework won't be due until the next Friday after that.